Vectors can also have their own functions for their components. For example, we can have r of t is equal to x of t, y of t, and z of t. And each of these, so long as the rules of differentiating apply, we can find the derivative, and each component would have its own derivative. So if we wanted to find dr by dt, or r prime of t, remember this is a vector, r prime of t, then this would be x prime of t, y prime of t, and z prime of t. This is assuming that each component is differentiable at a certain point. In addition, vector derivatives basically apply the same rules of differentiation as before. It's just that now each component will be added instead of the whole function. So, this component can only be added with a component like that. This component for that one, that component for that one, that component for that one. So the x components and y components and z components all get added separately. Because vectors are a little different than functions. Oh, I madly messed that up. That's just supposed to be a prime. Because vectors are a little bit different than scalar functions, we can actually have something like f of t and a of t, and we can actually put a of t as components. Let's say x of t, y of t, and z of t, and that's getting multiplied by the function f of t. And then we want to differentiate that. Well, we're going to have to do the product rule for each individual component, because it'll look like f of t, no comma, times x of t, comma, y of t, f of t, comma, z of t, f of t. And if we wanted to differentiate that, we can. Each one will be a product, and that's not exactly too hard, but it is doable. So remember, it's f prime x plus x prime f, comma, y prime f plus f prime y, comma, z prime f plus z f prime. And that's how you would take the derivative of a vector valued function multiplied by a scalar function. Now we can also differentiate a dot product, surprisingly. Let's say we have a dot b, and this actually looks a lot like a dot product, but for it looks like a dot product rule. So what this is now it's a prime dot b plus b prime dot a, and this also applies to the cross product, a cross b. now we would get A prime cross B plus B prime. Well, actually, the order should stay the same. A cross B prime. And these are derivatives of the entire vector valued function. And then there's also the rule, if we have a f of t, this is going to have a chain rule, f of t times a prime of t. And I've never really used this before. It's like an inner and outer function, much like in single variable calculus, but I never really encountered this very much. But yeah, that's the basics for differentiating vector valued functions. We said that we have a vector valued function, r of t is equal to x of t, y of t, z of t. We can differentiate each component, and that's fine. If we multiply by a scalar function, we get this bad boy, where each component is a product rule now, and that's not too bad. We can differentiate a dot product and get a prime dot b plus b prime dot a, and then we can also do the cross product, and then we can have like a chain rule. And that's about it. Thanks for watching.